Assalamu alaikum. Today we are going to start chapter entitled Signal Conversion and Processing. Digital signal processing is a technology that is widely used in many applications such as graphics, imaging, industrial instrumentation, medical, military, telecommunications, and voice speech applications. It incorporates mathematics, software programming, and processing hardware to manipulate analog signals. Of course, it is a vast field, but don't worry, as we will focus only on basics and some signal conversion methods. So at first we will study analog to digital conversion. So in order to process signals using digital techniques, the incoming analog signal must be converted into digital form. Before going into depth, we have to understand some basic concepts like sampling and filtering. So what is sampling? Sampling is the process of taking a sufficient number of discrete values at points on a waveform that will define the shape of the waveform. It converts an analog signal into a series of impulses, each representing the amplitude of the signal at a given instant in time. The more samples you take, the more accurately you can define a waveform. So here you can see illustration of the sampling process. We want to apply sampling process on an analog input signal. You can see here analog input signal. A sampling circuit needs two inputs, one analog input signal and second sampling pulses, and gives a sampled version of input signal here, in which each impulse represents the amplitude of the signal at a given instant in time. Here you can compare these two waveforms and you can see this is original analog input signal and this is sampled version of input signal. So you can compare the amplitude. The sampling theorem. It states that in order to represent an analog signal, the sampling frequency must be at least twice the highest frequency component of the analog signal. So if f sample represents the sampling frequency and the highest frequency component is Fa maximum, we can write the sampling theorem equation form as it is. So Fa maximum is known as Nyquist frequency. So what is the significance of this theorem? All analog signals contain a spectrum of component frequencies. The harmonics of an analog signal are sine waves of different frequencies and amplitudes. When the harmonics of a given periodic waveform are added, the result is the original signal. So it is very basic, you know it very well. Before a signal can be sampled, it must be passed through a low pass filter, anti-aliasing filter, to eliminate harmonic frequencies above a certain value as determined by the Nyquist frequency. So if the analog signal contains frequencies above the Nyquist frequency, these frequencies overlap into the spectrum of the sample waveform and interference occurs. You can see this phenomena in this figure. The lower frequency components of the sampling waveform here become mixed in with the frequency spectra of the analog waveform. So this blue line shows unfiltered analog frequency spectrum, this one, and this red line shows sampling frequency spectrum. And in this shaded area you can see that this overlapping causes aliasing error. So how can we avoid an aliasing error? The filter must at least eliminate all analog frequencies above the minimum frequency in the sampling spectrum. So after filtering, you can see that now again this blue line shows filtered analog frequency spectrum, and this is sampling frequency spectrum. So now there is no overlapping area. So basically this is the same thing, same interpretation of sample theorem. Aliasing can also be avoided by sufficiently increasing the sampling frequency. However, the maximum sampling frequency is usually limited by the performance of the analog to digital converter that follows it. So we will study this analog to digital converter ADC methods inshallah in next slides. So after sampling and filtering, the next step is to hold the sample value. The sample level must be held constant until the next sample occurs. Why this is necessary? Because for ADC to have time to process the sample value. Of course, the next stage will be ADC. So, ADC will convert these signals, these sample values one by one. So, you have to give enough time to ADC to process the sample value. This sample and hold operation results in a stair-step waveform that approximates the analog input waveform as shown below. So here you can see this is our original analog signal to whom we want to convert into digital form. This is sampling waveform. So this is our sampling equipment. Two inputs are given. One is analog input signal, second is sampling waveform, and then the output of this sample box is going to the input of hold box. So this is sample and hold equipment. So here you can say that the output of the sampling process is shown here, sample version of the input signal, and this is the output of the sample and hold approximation of input signal. So here you can see that it is a stair-step waveform. Of course, when you are going to hold something, so it will appear like this. After studying some basic concepts, let's come back to our target, that is analog digital conversion. So how can we define it? It is the process of converting the output of the sample and hold circuit to a series of binary codes that represent the amplitude of the analog input at each of the sample times. The sample and hold process keeps the amplitude of the analog input signal constant between sample pulses. So figure below illustrates the basic function of an analog to digital converter, which is the circuit that performs analog to digital conversion. So what is this? This is the output of sample and hold circuit. That is, it is stair step. So we give this to ADC, and the output of ADC you can see here is the binary values. So what is quantization? The process of converting an analog value to a code is called quantization. The more bits that are used to represent the sample value, the more accurate is the representation. So here in figure below, let's quantize the reproduction of the analog waveform into 4 levels, 0 to 3. And of course, for 4 binary numbers, you need 2 bits. So each quantization level or code is represented by a 2-bit code on the vertical axis, and each sample interval is numbered along the horizontal axis. And you can see here that of course for all these amplitude levels we have only four numbers to represent, that is 0, 1, 2, 3. So all variations in the input signal, you have no other option, just only four numbers. And here data is quantized to the next lower level, as in case of sample 3. Just focus on it. We have assigned quantization level 2, and for sample 4 we have assigned quantization level 1, that is next lower level. For this value next lower level is 1, for this value next lower level is 2. So of course you all have books, so you can see that here is a table for all these values, and you can verify from this figure and also from that table. So here in this figure you can see that if we use 2-bit digital codes to reconstruct the original waveform, accuracy is lost. So here you can compare that if we reconstruct the original waveform, and of course we will use digital to analog converters, we will study later, but you can see here that accuracy is lost. Now let's see how more bits will improve accuracy. So this figure shows the same waveform with 16 quantization levels, that is 4 bits. So here you can see along vertical axis, now we have 16 numbers 0 to 15 to represent the amplitudes of the same waveform. So what will be the impact if we want to? So here in this figure you can see that we have used 4 digital codes to reconstruct the original waveform, and the result is much more like the original waveform. So we can see that greater accuracy is achieved with more quantization bits. So I think it's simple concept, not so difficult. However, if you have some problem, I am online with you, and you can send me voice messages, and you can also type your messages. So we will discuss it inshallah. So let's discuss it, and then we will move ahead inshallah.